Hey everybody, welcome back. We've got an exam this week. So let's review for exam 3. It's going to work pretty similar to the other exam. You're going to have some quick timed questions. I'll ask you a few questions. You'll get a few points for those, and then you'll have it'll be you'll have about 2 hours or so to take the exam. Right? Once you get started, make sure you carve yourself out a nice 1.5 to 2 hour block to get it done. Answer to the best of your ability. You can make an A and not answer a single question if you very clearly show me you know how to get to a solution and get as far as you can on each problem. I mean, real easy to get to a C, and not too hard at all to get to a B without actually answering any questions, just as long as you show me you know how to solve the problem. That's really what I'm after. Given enough time, you would be able to answer any of them. That's the goal. It's not what I'm measuring. I'm measuring in a short period of time, can you identify the major concepts needed to solve a problem, correctly simplify them to an appropriate set of equations for your situation, and then put those together and communicate those in a fashion that I can grade and critique and understand what you're trying to do. So let's just jump right into it. This is for us in our text. This is chapter 6 and 7. It'll be 4 questions. Excuse me. I expect one of those questions to probably come from chapter 6, and the other 3 are probably going to come from chapter 7. They will be long. They will take their time. That's the reason I'll go ahead and give you the full 2 hours. At this point, you guys should be pretty good at scanning and sending a PDF, right? So you will lose points if you take more than 2 hours to load a PDF after starting a timed question. So what you might do is you guys hear my alarm go off in here when I'm recording videos, because I know my camera cuts me off every 15 minutes. So rather than just an abrupt stop in between videos, I try to make sure we get to a stopping place, or I quickly wrap something up and then start the next video. So maybe you set yourself a 1 hour and 50-minute timer. I mean, make sure that 10 minutes is enough to generate yourself a PDF, or if you think you can generate a PDF in 3 minutes, fine. Just set yourself an alarm for 1 hour and 57 minutes. I mean, whatever time you think it will take you to generate a PDF, set yourself a timer for that time, and leave yourself enough time. You will lose points in excess of 2 hours after you start a timed question, right? So I'm not going to, well, there's not going to be a time limit on the uploading of your entire PDF. There will be a 5-minute time limit on each of the time questions, but there's not going to be a time limit on loading your PDF. So anyway, that's kind of what that is. You're going to load the your PDF to the exam 3 assignment. Okay, so you'll have your timed questions, And then there'll be instructions that's going to direct you to loading your PDF to the Exam 3 assignments. That's where you're going to go to actually load your PDF. And the reason for that is I can actually grade and annotate it. I don't have to print your PDFs off and then grade the printed PDFs. I can just grade it within Canvas if you'll load those PDFs to the Exam 3 assignment folder. Okay, so that's the only change. Otherwise, it's going to look just like Exam 2, just different questions. But so anyway, if that's not clear, send me an email. I'll be happy to try to clarify anything that's not clear. Find me in the chat room, ask your questions. But it should look very much like Exam 2. Again, the only difference is when you load your final PDF, just go straight to the Exam 3 assignment and load it there. Okay? All right, so let's just jump right into it. So Chapter 6 talks about a couple of things. One of the main things it talks about is the concept of the heat engine. So a heat engine is a device where we have heat from some high temperature source at TH. That high temperature source dumps heat at a high temperature into a boiler, a heat exchanger. So maybe we've got hot air, or maybe we've got hot water. In the case of like a nuclear reactor, we superheat water. We run that water through a boiler, and there's a cold stream of water that gets heated up and turned into steam. So we have high pressure liquid water coming into the boiler. We have high pressure, high temperature steam going out of the boiler that we run into a turbine or turbine, and that turbine generates a power output. So this makes blades inside here spin. Those spinning blades then we hook up to a generator, and that generator we use to drive electricity or maybe a locomotive, whatever we want to hook up the output off this turbine up to. Okay, then from that, so what happens is the pressure drops, the temperature drops. Maybe you have just a tiny bit of condensation. You don't want much condensation in here. You want high quality steam, meaning like 90 to 95% in the vapor phase. So right at the point of saturation, get as much energy from here to here out as you can. Get it right to the point where condensation begins to occur. But if you have condensation in here, it's going to chew up your turbine. So you don't want much, but get as much energy as you can out. And then you're going to run this saturated mixture into a condenser. And the condenser is going to reject low temperature heat to a low temperature sink of some kind. Right? So some body of water or the atmosphere that can absorb heat and not notice a significant change. So the goal of the condenser is to get the fluid back down to a liquid state, because we need high pressure here, and this is low pressure down here. And so what we have to do is we have to increase the pressure by putting just a little tiny bit of power input into a pump. And it's real easy to do if I get this all the way down to a liquid, because liquid does not squeeze, it does not compress. So instead of a compressor, I've got a pump, and I put just a little bit of squeeze or a little bit of work into the pump, and that generates a large pressure increase. Then I've got high pressure liquid water ready to go into the boiler. That generates high pressure steam going back into the turbine. Okay, so if you look at your first law here, you've got QH, or we can say Q dot H. These are all, let's call them all dots. So Q dot H minus Q dot L, that's heat in minus heat out, plus a little bit of power input to the pump minus a lot of power output from the turbine. And that's going to equal 0. It is a closed cyclic system. So the idea is when we go around, there's no change in the energy for the cycle, for the system. And how we normally write this is we say, well, the net power output, the difference between work out and work in. So move this over. So it's work out minus work in over here on the other side of the equation, is going to equal the difference between the heat in and the heat out. That's QH minus QL. So the net work out, or the net power output, is equal to the net rate of heat in. The efficiency, the thermal efficiency for any heat engine, efficiency sub TH, the thermal efficiency for any heat engine is always going to be what we want, the net power output divided by what we have to do to get it. That's, in this case, Q dot H. This is what we're paying for. If we're using a fuel source or if we're using solar, then that's free, right? We have to pay to collect it somehow, some kind of collector, but this is what we have to supply. This is the difference between this and this is what we want. This is our efficiency. And again, if I plug this in here, this massages down to 1 minus Q dot L over Q dot H. And if we can achieve the maximum efficiency, and that only occurs with a reversible cycle, that's a Carnot cycle or any other reversible cycle. If it's a reversible cycle, and I can show you why this is true in just a little bit here, the ratio of heat transfers is equal to the ratio of absolute temperatures. The temperature of the sink divided by the temperature of the source. So the lower, the colder this is, right, the colder this is, right, so the higher this temperature is, or the lower, that's right, okay. that took me a moment to process in my head. If I notice what happens if this is absolute zero. If your sink is absolute zero and you can maintain absolute zero, that's actually kind of the third law of thermo at play. It says, well, you're not generating any new entropy if the sink stays at absolute zero, meaning you get 100% efficiency if this is absolute zero. Now, that doesn't make a lot of sense because as soon as I start dumping heat on a sink, the temperature is going to increase, especially if it's absolute zero. It's going to increase very quickly. But if I had a sink I can maintain at absolute zero, I get 100% efficiency. That's kind of cool. But that doesn't make sense. Now that would be why we would use liquid nitrogen to cool devices we need to operate at a very high efficiency. Get this very, very low. Right? If this is very low, then I'm subtracting a very small quantity, and therefore I'm closer to 100%. Or if I'm absorbing heat from a much higher temperature source, the higher the temperature of the source, the more efficient potentially our engine can be. That doesn't mean our actual engine is going to be more efficient. It just means potentially it could be. Okay? So that's a heat engine. The whole foundation of our civilization, honestly, and really the whole purpose of the science of thermodynamics is to try to get the most out of this type of device here, and this ends up being the conclusion of Clausius, Carnot, Kelvin, Planck. They all kind of reach this same consensus, and then we can talk about entropy and its implications there. Now, if we could run the reverse of a heat engine, that is what we call a refrigerator. Right? So a refrigerator, that's where, let's start with the compressor. I like to draw a turbo compressor, the reverse of a turbine. That's just me. This text likes to draw a piston cylinder. I understand that. If you look at traditional compressors in most refrigeration units, they kind of basically have a reciprocating piston cylinder inside, so that I understand why they would draw it that way. I don't. I draw a compressor where you start at, you feed in kind of at the wide end, and it squeezes it down to the narrow end, supplying a power input to do that. So the compressor, the idea in the compressor is you want to get the fluid, the refrigerant in here so hot, get it screaming hot, I like to say. Get it so hot that when we run it to the high side coils, the condenser coils, it will actually lose heat to a high temperature reservoir, the outside air, if you will. If we're trying to refrigerate the air inside a space, you want to reject heat to the higher temperature outside air. So the goal is to get the refrigerant in the compressor by squeezing it and adding energy to it, get it so hot that it'll lose heat to the higher temperature source. All right, we're going to pick up there on the next video. Hot.